Hello. Welcome. My name is Steve. I work for a company called Third Channel in Boston, in the United States. And I call this talk Reactive Streams and the Wild World of Groovy. I have a lot of slides to get through, so I'll still try and speak slowly, but if I'm going too fast, let me know. I should note that I gave a variation of this talk last year at Greach, but I believe that I've refined it a bit over this past year. I still don't consider myself an expert in reactive streams or Rx, but I'm more of a really big enthusiast. So I'd like to share my experiences so far with it. So first off, I may use the terms reactive extensions, reactive streams, or simply Rx, but they mean the same to me. I don't know if that's technically true, but I use the terms interchangeably. Anyway, so today I'd like to cover the following. First, I think every good presentation should start with the problem that this technology is trying to solve. Then we'll discuss reactive streams and go over quickly a couple of the Groovy tools that are available to us. Later on, we'll explore our Rx in depth, and at the end, I'll have a demo using those very tools that I talked about earlier. So first, the problem or the need to go reactive. Like, why is this important? But really, I think it's two problems. The first is that performance demands are always increasing. I mean, hopefully, right? The goal of you building up a website is to get more and more users using it. Yeah? But with all those wonderful users coming into your system, they're going to tax your application. They're going to take up resources and generally make a big mess of things. Also known as the stampeding herd problem, right? And yet, many frameworks that we still use to this day, still use technology and patterns that have been around since the beginning of web development. I think the biggest offender is a thread-based approach. So if a web server uses a thread pool for handling requests, where one request comes in is equal to one thread on the CPU, and that thread is consumed for the entire duration of the user's request. If that thread takes a long time, or it calls some I/O, or it blocks, or it waits in any way, that thread is occupied and cannot be used by anything else. This is especially a problem in a distributed system environment, where that request may need to communicate with other requests and generate many more. And just like a real pool, once you run out of resources, you're going to have a hard time. Things slow down. If your application can't keep up with user demands due to resource contention, your app will go really slow. And users don't like that. They get impatient and angry. And not only do they get angry, but they get distracted, and they may never come back. So this slide I took, and I use it a lot. I took it from a presentation by a Google engineer, I'm going to mispronounce his name, Ilya Grigorik. And he has this concept called the 1,000 millisecond time to glass challenge, which basically it's based on a psychology study that basically said when a user, it tested users' mental reactions when they interacted with the site, and if they performed an operation, depending on how long it took to get a response, would adjust it would affect them mentally. So if the user clicks on a button and the response is almost immediate, hey, it's fine. If the response comes with a 100, 300 millisecond response time, the user notices something's off, but hey, no big deal. 300 to 1 full second, there's a perceptible delay, and they start to lose focus on the task that they're doing. Anything beyond that, they get frustrated and may stop. Like if you've ever loaded a website and it takes forever, just give up and close it. So let's keep our users happy and engaged. So what to do? What can we do to help? We'll get into that in a bit, but as a hint, it's reactive streams. The second problem, or the challenge that I see ahead of us, is the rise of microservices, or really the rise of distributed environments, where our systems have a variety of additional systems that may have to interface with. So our main application may have to talk to other services in the platform, may have to talk to a database, it may have a third-party API it's got to communicate with, it's got user input that it has to handle. And so it's possible that we may end up having to write different handling mechanisms for each of these different inputs or data sources. And so, again, this is a problem of distributed environment, is that it's not only users that can take up the resources, but it's additional communication that can block your application and consume resources and slow you down. So what can we do? I firmly believe that some of the best techniques available to us now is async operations and non-blocking I/O. When a thread is not being used, it should not be blocked, but rather is allowed to be used by additional requests. We'll get that in a little bit in a moment, but it should also be stated that doing async is hard for us humans. It's not easy to think in terms of asynchronous behavior. So to help build robust sites, we need tools to help us go async and to read data from multiple sources in a common pattern. We need proper tools to help us. And I believe that, obviously, reactive streams are one such tool that can help us. So when I say reactive streams, what exactly am I talking about? So a reactive stream at its core is really just collections over time. So this is a sample diagram that you can find on this library called RxJava's website of the common zip operator. So the two upper lines are supposed to represent two separate collections and the time at which the data is available. I'll explore later about what this does, but this is more just to illustrate the concept of collections over time. It's also meant to be a single abstraction over data from many sources. So Rx attempts to unify how we handle data received from these different sources. I mean, obviously, the underlying driver for communicating with a database is going to be different from handling a third-party API, but once the data comes into your system, the goal with RxJava is to, or reactive streams in general, is to make one single way we handle the data as it comes in from different sources. And that's how it was originally developed. The reactive streams concept came out of Microsoft, believe it or not, from their cloud programmability team. They had all these services, and they wanted to find one way to make them all communicate together. It does this by making use of the observer pattern with a push, not pull-based iterators. Now, what's the difference? A pull is like if you have an array and you ask for a particular item in the array. So you say, give me the item at index 6. That you're pulling it out. An observer, or the observer pattern, pushes data at the user. So, or at the consumer. So it says, here's a data item, here's another one, here's another one, here's another one, etc. Rx is based, and you use it via stream-based functional programming. Now, what exactly do I mean by that? So here's a quick example of imperative versus reactive programming. No one, please notice that I put iterative instead of imperative. I realized that just now, and I'm very embarrassed. So in this example, you can see that at the top we just, we have an array of numbers and we iterate over it and we do some processing and then we print out the results. The same exact response happens down at the bottom, but it executes via a series of functions as opposed to this explicit, here's what I want to happen. It's subtle, and the purpose of this presentation is not to teach you that stream-based programming is great. At the end of this talk, there's a slide with a link to a bunch of different additional resources, and one of them is this excellent write-up by a guy named Martin Fowler about why just thinking in terms of streams is advantageous. And I encourage you all, once I post the slides, to take a look at that. Now, if that bottom example looked familiar to you, I'm not surprised, as Groovy's collection operators support some very similar behavior, as Garen mentioned this morning. So as an example, if this makes sense to you, then you're ready for reactive streams. I didn't know about that grep operator until I was putting the slide deck together. That actually, I don't know if you ever used collect and it returns a bunch of nulls into your array. The grep will actually strip all those out, which is very useful. One thing we haven't seen yet, and we'll get into, is why you hear the term extensions. It's because Rx provides extensions under the streams model for reactive-based programming. I mean, obviously. Anyway. In other words, Rx makes it simple to take a stream and then make it operate asynchronously. Finally, Rx provides support for backpressure, or something that's called, or the term that they use within the framework is reactive pull backpressure. And we'll get into that, what that concept means later. But this killer feature, I think, is it gives the ability of the subscribers who are receiving data, having it be pushed down to them, to communicate with observables when they're ready to receive more information from the observable. This allows us to prevent a client or subscriber from being overwhelmed by overproducing observables. And we'll get into what all those terms mean in a moment, but imagine something that's emitting data faster than the consumer can handle it. Rather than lock up the system and crash, the subscriber, in many cases, is able to communicate with the event producer to tell it to say, hey, slow down, I can't receive all that data. And there's a variety of ways that you can do to execute that behavior. Anyway, that's it from a high level. Hopefully that seems interesting. Let's explore it a little bit deeper. So one of the biggest aspects of Reactive Streams is that it can simplify some very complex work. Rx makes it easy to do some incredibly complicated and difficult work with very little code, once you understand it. Going reactive or using reactive streams is, unfortunately, fairly complicated and can be challenging until you get the handle of what's happening. Luckily, we have several tools available to us as Groovy developers. In fact, while reactive streams as a construct originated from within Microsoft, like I mentioned earlier, there has been a strong push from several large companies that are famously involved with the JVM, like Netflix and Twitter. These companies got together and created an organization to create a standard for Rx on the JVM. And there's a website they created called reactivestreams.org. That website publishes a list of all of the libraries and tools that adhere to the standard, and they offer a test framework, I believe it's called the TCK, that you can use to test your implementation to see if it adheres to the standards. The Groovy world has some heavy presence within this group, and there are several tools that we have that adhere to the Reactive Stream standard so far, and it's only been around for a few years now, so that's pretty good. We should probably start by mentioning RxJava, though. It is perhaps the most well-known option. Has anyone here heard of RxJava before? Right, it's most of you. It's pretty widely known. It was probably one of the first tools to bring the Reactive Streams to the JVM. It comes out of Netflix, and that's all great. But we should quickly ignore that and talk about RxGroovy instead, which is it's a library on top of RxJava, which simplifies things a great deal, I think. So as an example, this is roughly what a full Rx implementation would look like for a particular stream, or for a reactive stream that just does, you can't even see the top, that just does two things, a filter operation and a map operation. That's a lot of code. Now compare that with using Groovy and RxGroovy. It's much more concise, much more readable, much more elegant. You're able to clearly see what I'm intending here. I build an observable from an array of 1 to 1,000. I filter it for even numbers. I then square it, and then print out the results for every single item. Pretty simple. However, the most exciting tool right now, I think, that we have as Groovy developers is good old Ratpack. I hope everyone attended Jeff's talk this morning about Ratpack. It was very excellent. If you've not heard of Ratpack, it's a fairly new high-performance web framework. It's non-opinionated, but its most important feature, I think, is that it does not use the thread pool-based approach for consuming user requests. It's built on top of Reactive Streams, Netty, Java 8, Juice. It fully embodies the reactive paradigm. And as a result, it doesn't use servlets, for example, which is great. So you have these nice little lightweight, quick-starting, self-contained deployables. And there's a couple of the Ratpack developers in this room, so if I screw any of this up, talk to me later. So I blatantly stole this slide from a presentation by a guy named Dan Woods without his permission, so thanks, Dan. This is from a presentation he gave last year, which I couldn't put a diagram better myself together, so I just swiped it. It describes the architecture and how how Ratpack works. So basically what it does when you start it up, it spins up an event loop, which is the same, I believe, the same architectural pattern behind something like Node.js. But instead of just, Node.js has only got one, Ratpack gives you one per CPU core. And then when it accepts a user request, it passes off to a handler, and then if that handler has to wait for anything, like it has to make a blocking request to do some I/O, that particular position in the loop is freed up for another consumer to come in. So it, it utilizes as much of the CPU as it can without wasting resources. And those additional blocking I/O calls, I believe it does save a thread pool which is explicitly for standard I/O requests that it can make use of later. But I don't know. And then once everything comes back, then it responds, it goes back to the user. Let's see. So Ratpack also has the RxRatpack module, which I could go into, but I have a demo that shows it off, so we'll just explore that a little bit later. Besides these two, there are other tools like Reactive Streams and Project Reactor, which are great. But I've lately been spending my time with RxGroovy and Ratpack, so I'm just going to highlight those. So let's get a little bit deeper into what exactly is going on here. Or as much as we can get through in the short time that we have left. Please remember that Reactive Streams are a very complicated yet powerful tool, and I'd love to talk more about Rx after this talk, or throughout the rest of the conference. So before we go any further, we should probably talk about some key terms. So I've said the word observable a whole bunch of times now. An observable is like a promise plus plus. A promise or a future is a very useful construct for asynchronously accessing a single item. Observables are useful for asynchronously handling multiple items. That's why it's plus plus. An observable pushes items down the stream to its subscribers. That's the push versus pull mechanism. Subscribers receive and operate on the emitted data that they receive. In fact, this is part of the reason why we call it reactive. The subscriber is essentially waiting, and it reacts anytime data is passed to it. An observable, or subscriber, operates on what's called a scheduler. So this determines the type of async behavior. By default, a reactive stream is blocking and just runs in a current thread. But as we'll see later, it's very easy, almost stupidly easy, to instruct the stream to go async in a variety of ways. For example, I can tell the stream to simply spawn as a single thread and run a single thread, or I can spin up my own event loop for it in some implementations. I can use a thread pool, et cetera, et cetera. The schedulers available to you depend on the library you use. So Akka, for example, has a scheduler that allows you to use the actor pattern, because that's what it's based on. So with these terms out of the way, let's explore more about working with streams. If you were to build your own observable, here's a very, very rough outline of what it might look like. Note that we start out with a list of numbers, and we're doing some work on them. And then while we're doing that work, we call one of three functions on our available subscribers. We have an onNext function, an onCompleted, and an onError. OnNext is used for whenever it's time to send more data down to the user. So again, observables push data when they're ready, unless they receive some backpressure, which we'll get into a little bit later. But it's onNext, push data, so it's just iterating and just pushing data down. Once it's finished with processing that list, then it calls this onCompleted notion on the subscriber. So one key feature that I neglected to mention so far is that although we're working with a variety of sources, an observable has a convention for alerting the subscriber that everything's done. And there's no more data, go about your business. And then it can also signal that there was an error. So if something happened in the processing of the stream, it can alert the subscriber that, hey, something exploded. Let's see. So here's an example of a subscriber. A subscriber contains those same three methods we just saw. And I apologize, I didn't realize it would cut off the top of the slide there, but class, it would say new rx.subscriber. Let's see. So on completed, we say, hey, we're all done. I don't know why it's log error. Sorry about that. On error, yeah, we log an error. Oops. And then on next, we do some processing on the integer that we're receiving. And then there's a fourth method that's internal to the subscriber that signifies what to do when we start. And this is the first example of the reactive pull backpressure that we'll see. Because what the subscriber is saying is it's communicating to the observable that it says, hey, I'm ready, start sending data. So it's asking for the first item. Now that was a lot. There's a lot of code. That seems kind of onerous if I'm trying to assemble these things and work with them on a daily basis. So thankfully, there's a lot of shortcuts for simplifying how you create observables and subscribers. So this is a perfectly valid observable and a subscriber. That doesn't seem so bad, right? What we're doing here, the observable.from allows us to quickly turn a list of items into a basic observable. The subscribe function that's part of that stream takes a subscriber class, but in this particular variation that we can get with RxGroovy, I can simply pass it a closure, and it gets coerced into the subscriber class. So it's supposed to accept a class of func1, which is an internal to Rx. They also have func2, which is very originally named, and action. But the power of Groovy allows us to coerce closures into those functions without having to explicitly set them up, which is great. I should probably point out that, and it says right there in the slides, that passing one closure is equivalent to essentially passing it the functionality for the onNext action. So in that original observable, every onNext would execute that. Now, this additional example has 3 separate closures that map to the 3 functions: onNext, onErr, and onComplete. Very useful to know. This pattern we use in our code just about everywhere. Let's see. An observable doesn't always immediately need to be attached to a subscriber. I don't have to call subscribe right away. What that does is the moment I call subscribe, it makes the subscriber open and ready to receive data. And depending on the type of stream, which we'll get into later, I may start receiving data immediately. But I don't have to receive data immediately. I can compose my stream from a variety of other streams, and then when I'm ready, I can call .subscribe. So this is a trivial example. I basically start out with that observable of 1 to 10 in this case. I then create a new observable that's based on that original stream that applies 2 functions to it. Save that as a variable, which I can call independently. And then I create a third variable that takes that intermediary observable, adds another function onto it. And then at the very bottom, I call subscribe or introduce. I could call subscribe on the very first stream. I could call subscribe on map and filter, and only have the functionality that was saved as part of that stream, if that makes sense. These can be mixed and matched and combined. I could create a shortcut, like if I do a common filter and map operation, I could create a function or a utility that simply attaches that to any stream I feel like. You can get a lot of power just out of 5 functions. Now, keep in mind that RxJava and the Reactive Streams type, there's many, many operations you can do to these streams. But when you first get started, you're mostly just going to be using these 5. So, to quickly go over them, the filter function is exactly what it sounds like. I start with an observable, and then only items that pass some sort of truth test will continue down the stream. The function closure, at the function receives the item, so the function closure that's part of filter receives the item from the stream and then must return a Boolean argument to determine whether or not that item is allowed to continue down the stream. The map function is straightforward and highly useful. Map allows you to perform some operation on an item. You're probably going to use this one quite a bit. You must return the item to continue down the stream. The closure accepts the item that's coming down the stream. Map is extremely useful for data transformation. So one key point is that a stream may start with one type, one class of object, and then end up with a completely different class. Then map is useful for doing that transformation. I could, example, start with a stream of strings, and then use map to turn them into a map. Reduce. You may use reduce when you want to reduce the stream of items down to some sort of single object. Now you could use it to turn groups of items into a list. Here I'm summing a set of integers down into one value. I could build up a map based on a stream of database records, etc. The function accepts 2 arguments. The initial value of an object, and then the second argument is another function that also accepts 2 arguments. The first one is the object you're reducing into, called the accumulator. And then the first argument is the initial state of the accumulator. And then the second argument is a function which accepts two arguments itself. The first being the current value of the accumulator, and the second one being the instance of the item. I realize this may be a little bit confusing because it's two integers, but anyway, this order gets me every single time. So I will type this out, and I always get confused which one is which. Let's see. So the closure should take the item and place it somehow into the accumulator, and then return the updated accumulator object to keep going. If you screw this up, it'll blow up right away, so you'll know that you're doing something wrong. So this next one, group by. This can be a little confusing. Group by allows you to split up your stream into a number of streams based on the filtering criteria, or the grouping criteria. This then allows you to perform actions on groups of items that you can be sure are all alike based on some criteria. So in this case, we split our stream into however many unique years we have in this book list variable. This, I think, is the first big mental challenge that you're going to run into when you work with streams. In this example, I've basically taken a observable and turned it into an observable of observables. Which, whoa, what do I do with that? I just want my books, right? So I apologize, this is a bit hard to read. So the tricky bit here is that group by actually splits your single observable into multiple observables, each emitting only those items which have been bucketed into them, if that makes any sense. So let's say that book list had books that only spanning 4 years. So I would get 4 streams, let's say 2016, 15, 14, 13. And so I'd have an independent stream with only those books contained within that year. Follow me so far? So I can then perform additional operations on that stream, just like it was part of the main stream. So each of these arrows represents a bit of data flow. So I can do additional operations on these inner streams, and then once I'm done, I have to merge them together back somehow, because I can't do much with just a raw observable object in my subscriber. So how do I pipe these back in to my outer main stream? Now, a function called flatmap comes to the rescue. It's commonly paired with group by, but it doesn't have to be. So what flatmap does is take it expects you to return an observable, but it doesn't have to accept one, which I'll talk about in 1 second. But in this particular case, flatmap is useful for taking where is it, right up there? So I call the group by, and now I have my individual streams. The flatmap is now accepting it's accepting a stream of observables. It then, inside itself, calls 2 functions on that observable. So let's say that year group contains year 2015. I'm then going to do a reduce and sum up the number of books that were just in 2015, if that makes any sense. Then map them into a string that has the count and then the year. That year group dot key, it's actually a method called getKey, but yay groovy, I can just say key, is a unique parameter to the observable that comes out of group by that allows me to access the criteria that the things were grouped by. So in this case, because I'm splitting by year, the key for the year group is the year that's of the items that are in the current stream. Does that make sense? Okay. Then at the end, I simply call subscribe on the outer stream. So this last return value, if this wasn't RxGroovy, I'd explicitly have to say return year group reduce map. But this because this is the last argument, it gets returned, and then goes back to the outer stream, and flatmap takes that observable and essentially squashes it down to emitting each item that comes out of that. It essentially merges as the events come out of these grouped observables, it merges them back into one observable. Easy enough? Now, this is going to get a little crazy, so please don't be afraid by how dense this text is. So, because those inner streams are streams themselves, I can group further and keep going down that rabbit hole and keep grouping as far down as I want to. So, while this is very dense, if you look at it for a second, I think what's nice about the streams is that because it's all functional, I explicitly know what's happening, or I can just read the function names and have a vague idea immediately of what's happening. So I know that I'm grouping, I know that I'm flat mapping, I know that I'm grouping, flat mapping, reduce, map, and subscribe. So to look at it another way, I can tell immediately that I'm making two groups and then combining them all somehow and reducing them and grouping them back down into one object. This is common if you're doing some sort of analysis on a stream of data types, or in our case, we're a big fan of a term called event sourcing. So we pipe a lot of events down through streams and then do some sort of analysis on them in order to get some end result. In this particular case, what we're doing is, just like in the previous example, grouping by year, and then grouping by genre of book. So if it's a horror, it's a sci-fi. And so now we have a count of each genre in each year, or the streams are now a count of a genre for every year. Does that make sense? I then can reduce that down into a map that contains the count of each genres, and then reduce that, and it's a map of one key, the year, and then which contains itself a map of all the genres, and then reduce each of those years down into one big map. So this would essentially print this particular output. So if I only had 2 years, let me say 2016, count the sci-fi, count the drama novels, 2015, horror and mystery. Weird, huh? Note that reduce doesn't work with a type of stream called hot. So now's the time we're going to talk about the two different types of streams available to us, hot and cold. So a cold observable, pretty much all the examples I've shown you so far have been cold observables. If you start playing around with RxJava, you're probably mostly going to be working with cold observables. A cold stream is a set of finite data. For example, a list of books that I pulled out of the database, a set of numbers, an array of a finite array. And those items are available to us on demand. Typically what happens is, in a cold stream, as soon as your subscriber finishes, it immediately requests for the next object to be sent. And it's typically, like I said, created from some sort of collection. The hot observables, on the other hand, are kind of confusing. So it's potentially infinite data. I should also say that the cold observables signal when they're done. The hot observable, while it could signal when it's done, most of the time the hot observable will be around forever for the lifetime of your application, and potentially have infinite data and emit it when it's ready. So you could create an observable around, say, a user's mouse movements when they're moving the mouse around. You may subscribe right away, but you may not get any data right away, so you may be sitting there. And once user starts moving, you might sporadically get mouse events. This is what we've all been building up to. I've been telling you that reactive streams make async easy. All these previous examples I've shown you, they've all been synchronous. So what to do if I want to go asynchronous? It's pretty easy. If I want to have my subscriber operate asynchronously, I simply have to add a .observeOn function and then provide it the scheduler, as I mentioned earlier, that I want it to function on. So in this case, I'm using computation, which I believe maps to an event loop, but not particularly sure. The schedulers available to you depend, again, like I said, on the library they're using. So Reactor has some slightly different schedulers than RxJava does. It's a little confusing because it says observeOn, but it affects the subscriber. It always confuses me. Now, the thing to realize is that the observer and the subscriber can function independently of each other. So I may have an observable that collects data asynchronously and passes it to a synchronous subscriber, and vice versa. So if I want to tell the observable to be asynchronous, I simply add the subscribeOn function, which again is confusing because the subscribeOn affects the observable. Hey. And I can do both. I can make a stream that has a async observable and an async subscriber, and really go nuts. So the next section, backpressure. Backpressure, like I said earlier, is the ability for the subscriber to communicate back to the observable that hey, slow down, or hey, I'm ready. Keep the data coming. Now the example, it's not magic. but it can be a little confusing, and it's mostly, weirdly, only available to you when you're using a cold stream. Because you can't, hot stream, you can't guarantee when the data is going to be available to you. So there's things you can do, which we'll get into in a moment, but with an observable, or with a cold observable, it's pretty easy to illustrate. This is an example of what's known, according to the RxGroovy docs, as a reactive pull backpressure. So my subscriber starts out by attaching itself to the observable and says, hey, give me 10 items. And the observable goes, yeah, here you go, here's 10. And then a little bit later, once the subscriber's done processing those 10 items, it goes, oh, just give me one. The subscriber goes, okay, here you go, here's one. The subscriber then, once it's finished with that one, says, okay, give me 5. But the observable, it's only got 3 remaining, so it says, oh, hey, sorry, I've only got 3 remaining, oh, and by the way, I'm done. So that's a trivial example of how reactive pull works, where the subscriber is essentially, saying, hey, I'm ready, give me some more. Hot streams, though, it's a little bit more difficult. It's you can't communicate directly to the user to say, hey, slow down with your mouse movements. It's a little bit tough. So what you can do with hot streams, RxGroovy provides some functionality out of the box. There's a few operators. One's called throttle, which tries to group the events by over a time period. Same thing with sample, or maybe that's window. There's also 2 built-in functions you can attach to your stream on backpressure buffer, where if the resources in the subscriber are reaching a certain point, the subscriber will try and buffer the results and hold on to them later. That can be dangerous because the buffer can fill up and then your machine can crash. There's also drop, which is dangerous. Drop basically says, okay, when things start getting crazy, start just dropping events, which you may not want to do. You may care about some of that data that's coming in. Let's see. So this last feature that I want to talk about is Rx's ability to have observables interact with each other. Now, this is something that blows my mind, and it's a little confusing, but I'll see if I can explain it. So a phrase or a sentence to remember when we start thinking about this stuff is this is from a man from Netflix by the name of Jafar Hussain, who gave an excellent presentation on using Rx in the front end. And there's a link at the end of this deck if you want to check it out, and I highly encourage watching it. It's only about 20 minutes. It's great. But he says, don't unsubscribe from observables. So remember that a subscriber can subscribe, and there was that check earlier to see if it was still subscribed. If you're, especially with hot observables, you can stop listening at any point. But instead, programmatically complete them when another observable fires. Oh, okay, what does that mean? So as an example of what that phrase means, Jafar talked about how Netflix's type ahead works. So imagine for a minute, how would you build a type ahead or an autocomplete system now if your boss told you to go ahead and build one? And what if it had these requirements? You had to wait 250 milliseconds between key presses before querying. So if these are types A and then pauses, do a query. But if they type THE real fast, just do a query with THE, not a query for T and H and E. Does that make sense? If no keys are pressed, I don't want you to fire any queries, so don't fire one every 250 milliseconds. That would just be wasting, resources. Successful queries should render movies, obviously. But this is the kicker: new queries should kill in-flight queries. So if I start typing, pause, and then type again, and my second query goes out before the first returns, I should not render both the results with the first and the second query. Does that make sense? Everyone got all that? Like, how would you put that together, right? You would need to set up a loop for every 250 milliseconds. You'd have to set up a lot of once handlers. You'd have to turn them off when the response comes back. It would probably look pretty gross, right? How long do you think that would take you? With streams, it's about 5 lines of code, right? So this is pseudocode, but I promise you this works, and I'll show you an example. Hopefully, I've got 5 minutes left, so let's see if I can get to it. So what I'm doing here is that key presses variable is a stream that's watching the input box that the user types into. It then throttles the request for every 250 milliseconds, and then if events are emitted within that 250 gap, it emits those items. It passes them to a map method, which then calls a getJSON, which is in itself a stream. Then it retries for safety in case something explodes. And then that command take until, I forgot a period, please excuse me, that take until command, until key presses, the stream it's listening to emits an item. It then groups all those items, and then the search result sets is itself a stream, which then gets called by the function down here to actually do the rendering. So the key bit there is that take until. So what's happening there is that, so the black lines represent the user request, and the red represents the response comes back but was ignored. So if you start typing, then a response comes back. But if you start typing before the response comes back, that handler is automatically killed. So that take until, if another request comes down from key presses before the get JSON completes, that get JSON stream will be canceled and just stopped. So the handler will go away. It will automatically stop listening, all automatically, without you having to worry about an event handler at all. It's pretty slick. So an example of how that works, let's fire up a quick example. I've got 4 minutes. This may not be as nice as we might want. So hold on, bear with me. Okay. So this is a app that I built using Ratpack, RxJS, which is a library for the front end, and RxGroovy. So welcome to Rx Movies. Let me start typing. So I type T, doesn't do anything. H doesn't do anything. A doesn't do anything. Oh, wait, I got some movies. So I start typing the H. Oh, come on. Then I got the Hateful Eight. I can type The Martian, start typing The Martian. I can start typing Duo. I got Goosebumps and The Good Dinosaur, but if I type a D, it goes away. Delete it, comes back. And then it all goes away. Pretty slick, right? The code for doing that is not that. That's a JSON database or a JSON data file of all those movies. Here we go. That's much better, right? Let's see if I can make that bigger. Oh, come on. So this is a re-implementation of that slide I had there earlier. So I slapped an observable onto the autocomplete input, listening for key up events. I throttle it for every 300 milliseconds in this case. I save it as a stream, and then I compose it into 2 additional streams. The bottom one, which filters out any key presses that are under a search threshold, so under 2 characters. So if the box is less than or equal to 2 characters, it won't display any results, and in fact will clear it. The other stream filters out any key presses that are longer than that threshold, and then it will execute that get JSON command. I didn't do the retry, because whatever, and then it takes until the stream emits data again. It then concat all, which is RxJS's version of flat map. So it's passing a single stream. It then calls subscribe with this class that then actually renders the movie. Any questions on that? That is JavaScript code. So it's actually ES6. So I'm using Babel and Webpack to basically take that. So I wanted to make it extra small for you, so I'm using ES6 to use their Lambda functions. Anyway. Anybody else? Okay, let me show you what's happening on the back end. So just like how we do it on the front end, the back end is also stream-based. I should probably show the Ratpack, because we're here. Let's see. I just want to point out, Jeff, that I'm using the separate files that you pointed out this morning. So instead of putting everything in the ratpack.groovy, I have a separate, essentially, it's an action chain, which I have my different endpoints put in here. So then I have this movies API. Whoops, that's embarrassing. So I have this, should probably have closed Chrome or closed Facebook. So then I have this movies API, this movies API endpoint. It on GET requests, it starts up the data objects there for just timing from my own ends to see how long these things are taking. Incidentally, it's like 3 millisecond response time. It's fantastic. So I basically take the data as it comes in from the AJAX request, parse it, and then Ratpack this Ratpack implementation, which I forgot to mention. I don't really have time. Whoops. So the Rx Ratpack module, it adds a, you have to call it before you, when you start Ratpack, and it adds a custom scheduler to your Rx streams that allow them to be operated and maintained by Ratpack. And what that all means is it's always automatically async. I never have to add the subscribe on or observe on, which is pretty useful. So this particular request, I receive the data, I turn it into observable. This single check ensures that I only have one response. So in case it's sort of like an assert. I then map it into this thing I'm calling an API query, which then goes into this repository service to process results. Then I return, and that process results. The interesting bit here is it's using this zip operator to make 3 separate parallel stream operations to get both the movie list, the year breakdown, and the genre breakdown. So that zip function is doing 3 separate streams. And the way zip works is it waits for the first response, the nth response from each stream, and then emits that as an object, or as an item, which is extraordinarily useful if you're only getting one item back. It's very useful also if you have multiple, but you have to be careful. If you have one stream that returns quickly and other streams that return slowly, it can block things. Anyway, we're getting out of time. I go into this more in depth, but I'm already over. So with that, does anybody have any questions? Yes?
Will you share that source code?
Yes. So that is actually the first link on this more information slide. So I'll post the slides when I get out of here and tweet it out, and I'm sure it'll be available as part of the Greach materials. Anybody else? No. All right. Yeah. Definitely take a look at the demo if you're interested in this at all. There's a lot of different ways that streams are being used, both in the front and the back end. And I hope you enjoyed it as much as I do. Thank you very much.